guess the 10 or so of us, we'll continue on anyway. So we're going to start out with some review from last time. So I got a couple questions in a row for you, if you're able to join. Hello, welcome. The rest of the class planned to party without us, I guess. Oh, well. Okay. So quick review from last time. All right. So first thing, we got to remember what compliance is to understand the values that we're about to go through. Okay. So high compliance is what we want our lungs to be. So we want them to expand easily, have big changes in their volume, even when we just exert a small change in pressure using the musculature of our thorax. This is good because we don't want to have to work too hard to breathe. Okay. So our second piece, a little bit of review. We talked a little bit about resistance and therefore some factors that affect bronchodilation and bronchoconstriction. Okay. So bronchodilation is going to make it easier to breathe, right? So that's our lower resistance with a wider bronchiole, right? So our airways are getting larger. And so the situations we want to see that in are when we're working hard, when we're kind of stressed out, when we're extra active from a metabolic perspective. So that's going to be when we have our sympathetic nervous system active, that fight or flight part of the nervous system, going hand in hand with epinephrine from your adrenal glands. And then we have also our carbon dioxide levels building up when we're active, right? Because we're producing a lot of ATP. So we got that waste product in our blood. We want to get rid of it. So this is also a helpful time to have those airways dilate so that you can breathe out that excess carbon dioxide. Okay. And finally, we went through some lung volumes and lung capacities, which is where we're going to pick up today. So we had a vital capacity, which we'll talk about again. Let's remember what it is. Okay, great. Yeah, so all of our capacities, we're going to be adding together volumes. So that's why we see little equations for all of these. Vital capacity specifically is all the air that you can move using your muscles. So you have your normal tidal breath, 500 milliliters, easy breathing. And then we've got extra on top that we could breathe in. That's our inspiratory reserve volume. And you've got extra that you could have breathed out. Probably didn't if you were easy breathing. So that's our expiratory reserve volume. So all of those together are our vital capacity. So the amount of air that we can deliberately move in and out of our lungs. Okay, awesome. We have a bunch of perfect scores here. Okay, so reminder to look over these volumes and capacities, and we have them summarized here in this graph. So total lung capacity would be if we added everything together, all right? What we just looked at was the vital capacity. So that's almost everything. What we're leaving out is our reserve volume. So that amount that you can't breathe out, that's just holding airways and alveoli open enough that they don't stick together, basically. As if they stuck together, we'd have to exert extra force to open them back up. Okay, and I didn't pull up this slide last time, although we talked about these quantities. All right, so we also can look at our functional residual capacity as a value. All right, so what that is basically the amount of air that's left in your lungs after normal tidal breath, so normal easy breath. So going to include that reserved volume, right? The RV, that's the part you can't get out. Plus it's going to include our ERV, our expiratory reserve volume. So the amount you could really force out if you tried, but probably aren't doing on a minute-to-minute basis. So that's our FRC. And then total lung capacity, just defined again as absolutely all the air that's in your lungs. Okay. So I'm about to ask you one more question as we go into understanding some of our pulmonary diseases. So you want to think about first, we're going to have different types of problems. So we're going to begin with, what if we have a change that makes it harder to breathe air out? Okay. Now take a look at the volumes. Remind yourself what they are, and then I'll click to a question. Actually, you guys probably have this slide in front of you, so I'll start asking. Okay. What volume do we think might increase if you're having trouble forcing air out? Okay, let's take a peek. Okay, cool. So I know we answered this probably because I used that word force air out. And that's true. So probably true too, that would go down a little bit if it's harder to breathe air out. Ultimately, I think you might be able to get the same amount of air if you push really hard, that expiratory reserve volume in the condition we're about to talk about. It would just take you longer. But what we're going to see in these diseases that cause more constriction of the airways, that we're often going to see that reserve volume building up, because as you try to breathe out air, usually you're not actually going to be able to push out some of that air remaining in the passageways, right? So what we're thinking about is a situation where we have higher resistance here in a tube. That's what we were going for with our, harder to breathe out kind of ballpark of our symptoms, right? So what's especially we may notice in patients is this reserve volume getting bigger, lifting up a bit as it's harder to push out your air. So I'm asking you this first because that's going to be one of our types of pulmonary disease that we're focusing in on. All right. So here we were looking at an obstructive pulmonary disease. All right. So that volume we were looking at was this one here. All right. And it does not seem natural to me how they've named this category of diseases obstructive pulmonary diseases. But what you want to think about here is these are diseases that affect resistance. So to kind of remember that, I think about like an obstruction in my airway, right? Like if you have something stuck in your throat, that would make the tube narrower, right? So maybe that way we can kind of link it up with our idea of resistance and our idea of airway radius, airway diameter. Okay, so in our obstructive pulmonary diseases, like asthma like COPD. We've got this trouble with resistance. It gets harder to move air out of the lungs because we're working with this narrowed pathway. So we often see that your patient or yourself, you're not actually breathing out all the air. Even kind of when you're trying, we often see that residual volume that's left kind of stuck in your lungs building up, creating an overinflated lung as you still try to move enough air to get enough oxygen and breathe out enough carbon dioxide. And along with that residual volume increasing, we see our functional residual capacity increase. So that one we are adding together our residual volume and that expiratory reserve volume as well for that functional residual capacity. So that also goes up. But in total, the amount of air we're moving per breath, even with our kind of forced breaths, our energetic breaths, where we use some energy, that vital capacity often decreases a bit with these obstructive pulmonary diseases. We'll see that that's also the case with the restrictive pulmonary diseases. So this is the piece that annoys me about their naming, because the restrictive pulmonary diseases aren't about resistance, even though this word restrictive looks similar. We're thinking about the size of the lung is what's being restricted in a restrictive pulmonary disease. So you're thinking along with, for example, lots of scar tissue on it. So this is why I was asking you about compliance. These restrictive pulmonary diseases are diseases where we have decreased compliance of the lung tissue. So it can't get as big. It's restricted in the total size of the lung because it's more difficult to expand this lung. And that means that overall, if your lung doesn't get as big as it did before, your total lung capacity decreases. So that was all our volumes added together. So absolutely all the air in the lung, as well as the vital capacity, right? So that air that you're moving, that you're able to move, also tends to be a lower amount than in a normal lung. Hopefully, not surprisingly. So I'm just going to pop those on to our understanding of the lung volumes and lung capacities. All right, so we're going to think first about increased resistance. So those are the obstructive ones. Oh, I think this is going to pop on in a second. Obstructive. Okay. Okay, so when we see these obstructive diseases, we're thinking about increasing reserve volume because you're not breathing out as much through that narrowed tube, even when you're putting some effort into it, which means that our functional residual capacity is also increasing, right? Because the reserve volume is part of that. So you'd maybe see this whole graph kind of like lifted a little, right? So if we were charting, maybe it would look something like this, right? So giving us that larger functional residual capacity. Yeah. And then we see our vital capacity decreasing, right? So we can imagine, again, on this made up line over here, right? You could see that the total amount of air that we're moving, right, here is a little less than in our normal lung capacities. Okay. So that's what happens when we have obstructive diseases, so making that airway too narrow. And then with decreased compliance, we see a lung that doesn't get large enough. So we see that same decrease in vital capacity overall, but it's now going to be because instead of going all the way up to the top, instead of having this total lung capacity and it goes there, we're going to be working with a lowered lung capacity. We're working with a smaller lung here, essentially. So along with that, right, total lung capacity is decreasing as well as our vital capacity here. Okay. So those are our restrictive diseases. Okay. Okay. So that's how they map onto our traditional lung volumes and lung capacities. But realistically, if you're in like a clinical setting, those aren't the tests you're going to be doing. I'm going to have two kind of tests that are related to those volumes and capacities, but also involve a little bit of a time element here, is what we can kind of think of as a difference. Okay, so for this first piece, we're going to have a forced vital capacity, which is going to be quite similar to our vital capacity, but now you're making a patient do it. That's this forced part, right? So you're going to have your patient breathe in as deep as possible, so the maximum volume inhalation, and then you're going to have them breathe out really fast as they can go, as deep as they can go. Okay. So you'll get a graph that looks something like this one up top, right? So we can see the time it took them, right, to breathe out specific volumes. This graph goes to 4 seconds here, right? So the forced vital capacity is focusing just on the amount part, right? So here we can see the forced vital capacity up there. And just based on this forced vital capacity, we can already kind of narrow down our lung function, because we remember, if we have an issue with compliance, right, our lung doesn't get as big as it should because that tissue is resisting it. It's a little too elastic. It's a little too tough to stretch out. So in a patient with a restrictive pulmonary disease, so those are the compliance ones, restricted in size of the lung, we're going to see that that forced vital capacity never gets up to our normal forced vital capacity. So here we can see where that forced vital capacity would be on these 3 lines overlaid. So we have normal lung function, this blue line on top. We have an obstructive disease in this green line highlighted. And then the restrictive is this purple one down low. So you can see this lung never got as big as the others. Okay, so that's a great way to tell immediately that you've got a restrictive pulmonary disease. But we're not totally done testing lung function just looking at that forced vital capacity. As we may notice that while we have some issues going on here in the obstructive pulmonary diseases, right? This doesn't look the same as normal, right? We do, at the very end, get up to at least near a normal forced vital capacity. So your patient would be working extra hard to breathe it out. It would take them a long time, but they'd probably get pretty close eventually. But that doesn't mean that their lung is working as it should. This doesn't mean that we've got normal breathing, right? So that's when we're going to look also at this forced expiratory volume, the FEV. Okay. So this FEV is where the time part comes in. Okay. So what we're going to be looking at for the FEV is we're going to look at how much air did they expire in that first second as you told them to breathe out all the possible air that they could, right? So we're going to see, right, in a normal lung, right, it's going to be like most of it, right? We're almost up to our forced vital capacity, even in that first second, right? So we're at 80% is our ballpark for normal lung function here when we're looking at these FEVs, okay? Now, if we look at the obstructive and restrictive pulmonary diseases, you can see they're both low at this point, right? So it's low because for the restrictive pulmonary disease, it's just going to stay low, right? Because that function, that forced vital capacity is lower, right? If we give this as a percentage, we're going to notice, because the obstructive pulmonary disease did eventually get up to around that normal lung forced vital capacity, what we're going to see is that this is a really small percent in the first second that was expelled, right? So low FVC is going to be our signal for the restrictive pulmonary diseases, so that total amount. And we're going to recognize the obstructive pulmonary diseases, the ones that have to do with resistance, as having a low FEV, right? Because it's a low percentage in that first second. This is about basically speed of breathing out, right? So less gets out in that first second. So we have values that we would compare these to as well, right? So FVC should be maybe 4,000-ish milliliters. So we're comparing it to breathing out like 3,200 in about a second for that normal lung function. Less than that, we got a obstructive pulmonary disease here. Another way you might see this expressed would be through our peak expiratory flow rate. So in this case, very similar to those FEVs, right? So we were looking at what percent of the air came out in the first second. Now we're just looking at, okay, an actual rate, right? So actual liters per second we're looking at. Right? So it's not a percent of that patient's total volume. It's just how fast is the air moving. Right? So in a normal lung, we're going to be somewhere in the 7 to 9 range, depending on population for that peak expiratory flow rate. Okay? And we're going to see that both the restrictive and obstructive pulmonary diseases have a lower PEFR, right? So lower peak expiratory flow rate. It's a little bit lower for the restrictive ones and a lot lower for the obstructive diseases. But in both cases, we'll see this dropping down because in the case of the obstructive disease, right? So this is our resistance one, right? So that's the lowest. All right. And that's why it's the lowest, right? Because our problem is in the size of the airway, right? So if our problem is the size of the airway, it's going to be slow going when we're looking at the liters per minute. For the restrictive disease, which is our compliance one, it's that we can't make that lung big enough, right? Which means we don't have as much air that we're blowing out. So we've got kind of a problem with our pressures and the amount of air that we're forcing out. So that's why we see a little bit of a dip with that one, but not as dramatic as with the resistance, right? Because we still are able to move air through that airway pretty good. We just don't have as much air to move. So those are the tests that you'll more likely see reported in like a patient chart or that your doctor might tell you to measure. If you're tracking some kind of pulmonary disease, you'll see those FVCs, FEVs, and PEFRs related to our traditional lung volumes and lung capacities, but a little specialized, a little easier to kind of measure on the spot. Especially because to figure out our reserve volume of our normal lung volumes, you have to use like helium dilution. So you have to be like making someone breathe in helium and then measuring how much of it gets used and into the lung and stuff. And that would be a pain in a doctor visit. Okay. So now we're going to be thinking, moving on from our diseases and our volumes and our capacities, we're starting to head towards our idea of gas exchange between the lungs and the blood. So to start this off, we want to think about how much air is getting to our alveoli on a minute-to-minute basis, okay? So to begin, we want to think about how much air is getting into our alveoli. We might just look at, okay, how much air did we move per minute? Okay, so our minute ventilation is what we're defining first. This is just how much air did you move over a minute? We're going to assume you're doing easy breathing, right? We're not doing any forcing of the air at this point. We're just looking at kind of normal, easy function at rest. So all we do for the minute ventilation is we multiply your normal tidal volume. So that's your normal breath, right? Just easy breathing. Times your respiration rate. So this is respiration rate. So how many breaths per minute? Okay. This is going to be something around like 10-ish usually. Yeah. Our number of breaths. Okay. So all we're doing here for our minute ventilation is multiplying how big was your breath by how many breaths per minute. Okay. But that's not going to get us quite as far as we need to go. Because we have this anatomical dead space, right? So we were just thinking about the concept of reserve volume, about the fact that we have that air we can't blow out of the lungs even if we try. But in general, when we're talking about the conducting zone, right, we have air in these passageways that's not participating in gas exchange, like even some of the air that you could move, right? So if it's in your trachea, you're not in your respiratory zone. We're not going to be moving air across the walls of our cells. We're not going to be getting into the blood. If you're in one of the main bronchi, any gas in there, it's not going to get into your blood. It's not till we hit the respiratory zone that we actually start doing gas exchange. So all of this anatomical dead space is going to be important to think about if we want to know, okay, but like how much oxygen are you actually getting from the air? Okay. So our usual value for the dead space is about 150 milliliters. Okay. And here's how we're thinking about it before we actually calculate out our alveolar ventilation, which is what we're going to do to account for the fact that some of the air in your lungs doesn't have nice, fresh, new oxygen in it. Okay. So we want to think about being in between breaths first, right? So when you're at equilibrium with the environment before you're moving air, right? At the end of that kind of like rest period in the middle, right? The alveoli, which is where our exchange of gases is happening, right? They're going to do their job. We're going to get oxygen into the blood. We get carbon dioxide into the air, right? So we can think of at rest, at the end of this little rest period, as this being kind of like old air, right? We used up the oxygen and we filled it with carbon dioxide while we were at equilibrium in between breaths. Okay, so then we're going to breathe in, right? So we're going to inspire. We are dropping down that pressure in the alveoli to suck air in, making them bigger. And here's what we can think of as happening. So think about this as a column of air, right? So the column being, right, some of it's in your trachea, then some of it's in those main bronchi, then some of it's in the segmental bronchi, and so on and so on and so on. Right? So when you breathe in, right, the air from outside immediately just goes into your mouth, right? So it's kind of stacking on top of the air that's already in your respiratory system, right? So here we see that as you breathe in, you do breathe fresh air into the alveoli, but you don't have a way to like get rid of that old air that was sitting around in the alveolus while you're breathing in. We just got one tube, the whole tube is going in. We don't have kind of a circle thing happening, right? So the air in the alveolus at this point is a mix of that old air plus some of our new air now, right? So new air ready for exchange. So here's where we exchange our carbon dioxide and oxygen again, right? So we're going to pull the oxygen out of this nice fresh air, fill it with carbon dioxide, and we can see that coming to equilibrium again here, right? Before we breathe out our air, right? So breathe it out, push it out, come to a sort of rest in between, come to equilibrium before we breathe in again. So when we think about our alveolar ventilation, we're not going to be able to think about just minute ventilation, just how much air did we move. We need to account for the fact that some of that air entering the alveoli doesn't have much oxygen in it and kind of has too much carbon dioxide. So that's why we have a separate calculation for alveolar ventilation. So minute ventilation, the easy one, just how much air per minute. Alveolar ventilation is getting us a little bit towards this gas exchange idea. So we have a piece of it in there still, right? So you might recognize we do still start by multiplying your tidal breath, so that typical easy breath of about 500 milliliters, right? By your respiration rate, so by your breaths per minute, right? So essentially this is our minute ventilation. But then we have to subtract away how much of the air that you were moving was old air, basically. So we're going to take our dead space volume next. And we're going to say, right, like every breath, you had some dead space in that breath. So we also multiply that times the respiration rate, right? Or you can imagine the equation isn't written this way, right? But basically we've just multiplied that respiration rate across both. So you might reshape it also as tidal volume minus your dead space, right? Times your respiration rate. That's the same equation here, okay? That's all we do. All right, so we're gonna do a practice problem here to make sure we got it. Okay, so we're gonna start with someone who has a normal tidal breath volume of 500 milliliters, okay? We're gonna make our math nice and easy. So they're breathing 10 breaths per minute. That's their respiratory rate. And they're gonna have the usual dead space volume of 150 milliliters. So we wanna know, okay, what is their minute ventilation gonna be in this case? And what is their alveolar ventilation gonna be in this case? Okay, we'll walk through it, but let's take a look. Okay, cool. All right. But I know we were missing some people, so let's go through. So we're going to start with our minute ventilation, okay? So for our minute ventilation, right, all we're doing is multiplying that tidal volume by their respiration rate, right? So we had 500 milliliters as their tidal volume, 10 breaths per minute, multiply them, right? So we got 5,000 milliliters, and we can convert that back to liters, so 5 liters. Okay? So that's our minute ventilation, pretty normal, okay? Our alveolar ventilation, we make our adjustments for the dead space volume, okay? So alveolar ventilation, we got two quantities that we're thinking about, right? The tidal volume and that dead space volume. And we're multiplying them both by that respiration rate. So we just calculated out this first quantity, right? So this first quantity is our minute ventilation in essence, right? You can see that's the same equation here, right? So our minute ventilation was 5 liters, okay? But we're not done because we have to subtract away this dead space, okay? So we start subtracting. Then we have to calculate how much of this was dead space volume per minute. So we got our value of 150 milliliters, okay? Multiply it by those number of breaths again. So we got 1.5 liters here of air was dead space volume. And now we can just subtract, right? So 5 liters for that minute ventilation minus this dead space times our respiratory rate, 1.5. And we get to our 3.5 liters here, right? So that's how we do it according to these equations in the book. But you might also notice, right, if you're trying to do it fast, you could just do that 500 milliliters minus the 150, right, get you to 350, and then multiply by the respiration rate, right? We just distributed it across in this equation, so they'll both get you to the same place, okay? So you're always going to have an alveolar ventilation that's less than the minute ventilation. That minute ventilation is always going to be higher because it's the one where we didn't have to do any subtraction. Okay, questions about this? Okay. So that's conceptually how we would measure this stuff in terms of volumes. Now we want to think about the gases that are in that air. So we can start to think about when you are moving air through your lungs, right? When you're doing this pulmonary ventilation, how much of that is actually getting to your tissue, right? And coming back to your lungs. So if we're thinking about that carbon dioxide, that waste product. So we have to spend a little bit of time thinking about gases and their properties, both in air and in fluids, which we'll do in a second. But we've got our like big picture overview here first, right? So we want to think about our lungs as part of a system, right? Talking to that cardiovascular system. So in this image, you can see here up top in the alveoli, we have carbon dioxide that we're breathing out, right? And oxygen that would be going in, right? Okay. It's going to circulate through your arteries, right? That oxygen is. And then we're going to use some of the oxygen in the tissue, because this was the point of moving oxygen through your bloodstream, was to actually feed your cells, right? So we have an exchange process here. We pull in oxygen, we put out carbon dioxide, right? So we're raising carbon dioxide levels in the blood as it comes back in the veins, and ultimately is going to get breathed out from those alveoli. Okay. So we can also notice on here that the amounts of carbon dioxide and oxygen being exchanged at the lungs and the tissue actually match, right? Ideally, we want to adjust how fast we breathe to how much oxygen do we want to feed that tissue and how much extra carbon dioxide are we producing, right? You don't want to hyperventilate, right? Because then you actually change the amount of each of those gases in the blood, and your body kind of doesn't like that, right? But you also don't want to breathe too slow. You don't want hypoventilation, because then you don't have enough oxygen and you have too much carbon dioxide. So we can notice that this carbon dioxide that we breathed out from our lungs was the same amount as the carbon dioxide that our tissue produced and put into your bloodstream, right? And the oxygen that we pulled into the lungs, right, is the same amount as the oxygen used by your tissue, right? So we're trying to make these quantities match when we breathe faster or breathe slower. It's kind of why you breathe faster and slower. So overall, we're going to see throughout like this chapter that the amount of oxygen and carbon dioxide you see in your blood is going to stay pretty constant. So long as things are working normally and you are adjusting your breathing as you should be, that's the point of adjusting your breathing, is so that we can keep oxygen and carbon dioxide pretty much the same, okay, throughout. So we'll have expected values of oxygen and carbon dioxide in our arteries, and then we'll have expected values of oxygen and carbon dioxide in the veins as well. Okay. We can also measure something called the respiratory quotient if we want. So we could look at that ratio of carbon dioxide that we're making, right, to this amount of oxygen that we're consuming, right? And this is another value that you might look at in a patient if you were trying to think about how is their gas exchange working? Are they clearing enough carbon dioxide and using enough oxygen? Okay. But before we get into all this stuff, we want to think about those gases and how they work, okay? So we're going to be thinking about diffusion of gases. So we already know the layers they have to cross, right? So we're in the respiratory part of our respiratory system. So we got those respiratory bronchioles, we got these alveoli in their alveolar sacs. We know this is mostly happening in the alveoli, and we know this is happening across those type 1 alveolar cells, right? So our type 1 cell we had to go across, right? And we have a basement membrane, which is basically just glue for our cells here. We go across a capillary endothelial cell, and then we're into our bloodstream, right? So that's our barrier for diffusion of these gases in both directions. So oxygen towards the blood, carbon dioxide towards the alveolus. Okay. Now, that's our barrier, but we're also going to see that the amount of a gas that you have circulating through your bloodstream is going to depend on how much of that gas was in the air, right? That's in the alveolus. And then also, how easy is it to get that gas into liquid form, right? So not all gases go into liquid as easily. Not all of them dissolve as much in your blood. So that's going to make a difference in these quantities that we'll track when we look at our oxygen cascade. Okay. All right. So our first piece that we're going to think about is how do we assess how much of a gas we have in the air? Okay. So to understand that, we got to think about our partial pressures of gases. So we're going to begin with our ideal gas law, which you may or may not remember from chemistry. We also mentioned this ideal gas law as we were thinking about alveoli and this trade-off between pressure and volume. Okay. So we used it for pressure and volume in the alveoli, and now we're going to be using it to think about quantifying gas percentages eventually in the air in the atmosphere and the air in our alveoli. Right? So we can give our pressure of a gas, right, as dependent upon the number of gas molecules, right? So this would be in moles, but number of molecules, right, of that gas. R is just a constant, but T is temperature. Right? And we know that we also have a volume, right? So that was how big are our alveoli. So if we give a pressure, it's going to tell us about all those three things together. Okay. We're going to see that we will actually be giving amounts of gas in the air, in your alveoli, and then also even in your blood as pressure values, right? So we're not going to see like milliliters of oxygen in your blood. Usually we're going to be giving those numbers as partial pressures, which is why we're going through this ideal gas law stuff in this partial pressure calculation. Okay. So to get to those numbers, we're going to realize that the gas in the atmosphere around us and in your lungs, pretty much the gas anywhere, is going to be a mixture of a bunch of different molecules, right? Unless you deliberately made just a canister of O2, which you would if someone's not getting enough oxygen, you might put them on O2. But if they're just breathing normal air, that's going to be some oxygen, it's going to be some carbon dioxide, it's going to be some nitrogen, right? So the pressure of the gas around us isn't just any one thing. Okay? So we're going to split out our total pressure and divide it into, okay, how much of that pressure is because of the oxygen? How much of that pressure is because of the nitrogen? How much of that pressure is because of the carbon dioxide, et cetera? So that's what we mean when we say a partial pressure of the gas, right? Is that we're recognizing that that total pressure in the atmosphere or in an alveolus is adding up a bunch of different gases together. You can calculate this by just doing a percentage, right? So if we have a total pressure, right, our partial pressure of that gas is just what percent of the air that we're looking at, of the gas that we're looking at, is that specific molecule. Right. So we will look at this in numbers as well to make sure that we kind of understand what this is instead of in just variables. Right? But our composition of normal air in the atmosphere is usually about 80% nitrogen, so technically 79, and 21% oxygen. So actually, most of the air around us is not actually made up of a molecule that you are using for respiration, for feeding your cells, right? Only 21% of it is this oxygen that we need. There are also trace amounts of carbon dioxide, helium, argon, all sorts of other gases, but not substantial amounts in the environment around us. Water is going to be its own thing. So water will play a big role when we're looking at partial pressures ultimately. You may have felt this yourself. I don't know about you, but like when I'm in a really humid room or in a sauna, right? Like I can kind of feel that that's changing my breathing. So we'll think about water vapor in a minute. But for right now, we're going to start out with just the nitrogen and the oxygen. Okay. So we're going to ballpark our total pressure in the air as about 760 millimeters of mercury, right? So that's like our atmospheric pressure here, right? So the total pressure of the air essentially is our atmospheric pressure. Okay. Okay. So that atmospheric pressure is made up mostly of pressure coming from nitrogen, pressure coming from oxygen. And to find the partial pressure of each of those gases, right? You're still going to have a big P for pressure. And now we specify it's a partial pressure by just putting what gas are we tracking in our subscript. And we just take a percentage, right? So 79% of that total pressure gives us 600 millimeters of mercury as our partial pressure for nitrogen. 21% of 760 gives us 160 as our partial pressure of oxygen in the atmosphere around us. Now, we're not calculating out carbon dioxide quite yet because it's only 0.03% carbon dioxide. Okay? So not a significant number out in the atmosphere, but it will become more significant as we get down into the alveoli. Okay. Now let's add on our water. Okay. So we're going to see even at 100% humidity, right, our atmospheric pressure is going to stay about the same, right? So we're going to keep that atmospheric pressure at 760, right? So this is not dictated by the number of gases. Right? Our atmospheric pressure worldwide stays about relatively steady. It just changes based on altitude mostly, right? But if you're in a really humid environment, that water vapor is like taking up space, right? So it needs to be accounted for when we look at the partial pressures. Okay? So at 100% humidity, our partial pressure of water vapor is about 47, okay? All right. So now 47 of that 760 is taken up by the water, okay? Which means that we can see that partial pressure of the nitrogen and oxygen dropping. Right? On the previous slide, we had nitrogen at a partial pressure of 600. Right? So now it's down to 563. We had oxygen, I think at 160. Now it's down to 149. In this case, if you're curious, we can still see carbon dioxide is almost nothing. Right? It's going to be at 0.21 here. So we'll pick up here next time thinking about how do we handle the solubility of gases in liquids and then put that together thinking about the alveoli as well as the capillaries that neighbor them.